everyone. Thanks for coming. My name is Ralf. I'm a software engineer at Amazon, and I would like to talk a little bit about dependency injection, and in particular kotlin-inject for Kotlin multi-platform. Before I get started, I want to give a little bit of background. I and my team are responsible for the in-van delivery app that runs, for example, in the Rivian delivery vans. And if you've never seen a Rivian, they have these large screens, and there's also some screenshots of our application running in the van with the dual screen setup. If anything of this sounds interesting to you, we are hiring. But more about what happens. Last year, I was here also in New York giving a talk about how we changed our architecture, how we changed scopes, how we do dependency injection, and how we adopted a unidirectional data flow. And part of this architecture was that we heavily rely on Dagger 2 and Anvil as a dependency injection framework because it takes away a lot of the boilerplate. It makes it very seamless and easy for us. So we don't really think about this anymore. And there was many good things that we liked about this setup. So Dagger 2 is great for us. It gives us a lot of safety in a larger code base with multiple teams contributing code. Anvil removes the boilerplate, makes the builds actually faster. But the issue we had this year is that we reached our goal of decoupling ourselves more and more from Android, but these two dependencies relied on the JVM, or Android in this case, and they didn't work for Kotlin multi-platform, which we wanted to adopt and roll out more this year. So we had to find a solution, and that solution is kotlin-inject. But before I get there, I want to do a quick recap of how we use Dagger 2 and Anvil internally and see then how this translates to kotlin-inject. So for Dagger 2, you usually have three components. You have a provider side. On the opposite side is the injection side, where you consume dependencies. And in the middle, you have the component that connects these two sides. Let's go through a quick example. Imagine you have an API, like a weather repository, that gives you the forecast for a given location. You have an implementation that maybe uses an HTTP client underneath. With Dagger, you provide this in the object graph through a module. And then you say, whenever somebody requests the type weather repository, they get an instance of weather repository implementation, and we make this also a singleton, so Dagger caches this for us. Then we can build our component, which is just an interface in Dagger speak. We add an annotation. We say, please include our module that we just created, so Dagger really knows how to use this weather repository implementation for this Dagger component. We make it a singleton, so Dagger makes the right associations with the scope. And that's about it. After that, Dagger will generate a new class. It will allow us to instantiate the component at runtime through the create function. And then we can start using the component. For example, we want to get an object out. Let's say we want to use our weather repository. That's fairly easy. We just add another method to our component, which returns the weather repository. And then we can call this at runtime. We can make this a little bit better. First of all, we can use constructor injection, which is convenient and removes more boilerplate. We just remove or add inject annotation to the constructor. With that, then Dagger knows how to instantiate the object, and we no longer need the provides method. We can also move the scope annotation. And with that, we can change Dagger module, the provider function, to a binding function. It removes a little bit of boilerplate. Let's have a look at the module structure setup. It's quite common for us, or actually it's something we strongly recommend for Dagger and kotlin-inject, to move the Dagger components into the application module. And this is necessary because usually all the feature contributes to your object graph. And then when you compile the Dagger components, Dagger has to know about all the code in your application. So that's the best place for it to be. On the other hand, the Dagger module, we created a weather repository module. This can be moved to a feature module. And this is how we start to decompose a little bit our object graph. Now, let's say we have another module, forecast, which would like to get the instance of the weather repository. Here we have a problem because we have a circular dependency. The app module depends on the forecast module, and then the application component lives in the app module, yet we want to call the weather repository function. And there's a very easy way to start decomposing the Dagger components. All you actually have to do is introduce a new interface, move the function to the new interface, and then make the Dagger component implement this interface. That's how you start to decompose the components for Dagger. And with that, Dagger will still generate all the necessary code at compile time, and things will work the same way. But for us, it means we can move this weather component interface into our feature module. And with that, we broke the circular dependency. There's still a lot of work. Anvil came here for us to the rescue, and I don't want to go too deep, just on the high level how it functions. I gave a talk with my friend Gabriel Pier 2 years ago of how Anvil itself works, and we go into all the details, what it does under the hood, more of the advanced features, how you can extend it, and so on. So if you want to learn more, I recommend taking a look at this talk. But on a high level, what Anvil allows you to do is contributing Dagger modules and component interfaces to your object graph. And then when it comes to compiling all the Dagger components, Anvil will merge all the contributions and add them to your component. And this adds a little more looser coupling. But still, at compile time, everything gets verified, and it's made sure that the object graph is still complete. This is how we would then translate our example. One way to do this is to say we contribute this Dagger module, weather repository module, to our application scope. But we can even go a step further and say, let Anvil generate the bindings method for us. What this contributes binding thing does is basically the same thing. It generates a binding method and adds it to the application scope. So this removes a lot of boilerplate for us, because this is a common pattern that we have. We have APIs and then implementations that are decoupled. The weather component interface from our forecast module from earlier, we just add a contributes to annotation to it, and then it will get automatically added. And that's how then our component evolves. We only have to change one annotation and define the application scope. With that, I mentioned the weather repository module is gone. It gets generated by Anvil, so we can remove this entirely. We can also remove this extra line, so our merge component definition looks like this. Then I also mentioned the weather component now gets contributed by Anvil, so we can remove this as well. So we removed even more code. Anvil and Dagger have been working really well for us, like I said, but we had this problem with we want to support KMP, Kotlin multi-platform. And that's where kotlin-inject came to the rescue. And the nice thing about kotlin-inject is that if you know Dagger 2, it works almost exactly the same way, but better. And because of all the similarities to Dagger 2, I would even go this far in calling it a Dagger 2 for Kotlin multi-platform, because it really unblocked this use case for us. And we will go through the example in a second, but the best part for us is still that we get the compile time safety. That's something we really look forward to. We like to see if we made errors in our dependency graph as early as possible, and compile time is the earliest we can get, so this is really great for us. Let's see how this example evolves. First of all, we have to create a new scope. Kotlin-inject doesn't come with a default scope like Dagger does from JSR 330, but it's not really a big deal. We just create our own. It's a new class and one annotation on it. This is the example how it looked like with Dagger 2. For kotlin-inject, the first thing we can change is we move the inject annotation from the constructor to the class, but in the end, it functions exactly the same way. It's just a little bit of syntax change. The Dagger module has to, or the kotlin-inject doesn't have modules. They only use components and rely more on the Kotlin language. So we turn this into an interface, but there's still a provider method, which functions very similar to provider functions in Dagger or the binding method that we had earlier. The component, there is still a component with kotlin-inject, but we no longer have Dagger modules, so we actually removed this, and instead add the weather repository component from the previous slide as a super type to our component. But in the end, it functions exactly the same way. Instead of a static function that we had from Dagger 2, kotlin-inject will generate a create function as an extension of the class object. Again, same thing, just a little bit of different syntax. The kotlin-inject doesn't have modules. They only use components and rely more on the Kotlin language. So we turn this into an interface, but there's still a provider method, which functions very similar to provider functions in Dagger or the binding method that we had earlier. The Remember earlier, we want to get the weather repository out of our object graph. It's almost identical with kotlin-inject. Here we just use a property that we then can call, and that's how we get our instance at runtime. Yeah, the problem we had with decomposing our component interfaces into multiple smaller pieces, that works also the same way in kotlin-inject. We can introduce the same weather component interface. We can then move this to our forecast module. We move the property into this, and then the same thing happens there. Kotlin-inject will still generate all the necessary code to make this work at runtime. So for our module structure, there were no changes at all. There are many good things we like about kotlin-inject, and one of the things I personally like the most is that it has a reduced API surface compared to Dagger 2. Dagger 2 allows you to do the same thing in multiple ways, and then these arguments start. Should I use this? Should I use that? Provider methods, binding methods, how do I create subcomponents? So it's a smaller API surface, but everything you actually need, so that's pretty nice. We like the fact, for example, how components are created and how you can pass arguments to components. Think of classes that you are not in charge of creating, like for Android, the application class. It really becomes just an argument on the component itself, like for a normal constructor argument. And with that, kotlin-inject will generate the code, and you have to pass the argument to the create function. Component inheritance or subcomponents and Dagger speak are the same way. They are just an argument for the constructor. Imagine you have, in this case, a logged-in component, which should also provide and have access to everything the application component provides. The application component just becomes an argument for our logged-in component, which is really neat. One pattern we like is creating factory interfaces in these subcomponents and then make our parent component implement this interface when there is this parent-child relationship. If we would do that and add now the factory interface as a super type 2 app component, then we would get a compile error from kotlin-inject because it doesn't know how to create logged-in component because it itself is a component. But what kotlin-inject also allows you to do is override functions manually. And that's what we use because on the caller side, on the usage side, things become a little bit easier. But we know how to create a logged-in component. And we tell kotlin-inject basically, don't implement this function for us, we do it ourselves, and then things work just fine. And there are other good things like lazy. The Kotlin language supports lazy out of the box. That's what they use. Or assisted injection, default arguments, they are all supported through the Kotlin language. Kotlin-inject compared to Dagger 2, vanilla Dagger 2 also builds faster. I want to highlight this real quick, what KPT, an annotation processor, does to your build. It adds a stub generating task, which is a subset of Kotlin C, where the Kotlin compiler turns all your Kotlin code into Java stub files. Then it feeds all the annotation processors with these Java stub files, which only operate on Java code. They usually then spit out Java code themselves. We feed then these Java files together with the Kotlin code to Kotlin C. And then in the end, we also have to run the Java compiler in order to generate our bytecode. With kotlin-inject, which is built on top of KSP, Kotlin symbol processing, it gets easier. There's a KSP task, which is similar to the job generating task. In that sense, it's a subset of Kotlin C, but here all the symbol processors run. They generate usually Kotlin code, and then we only need to run the Kotlin compiler and we're done. And if you compare this to KPT, this will be significantly faster. And also KPT is deprecated, so that's the future anyways. One thing I want to mention is that kotlin-inject is still evolving. It's not 1.0. The maintainer is open to feedback, open to discussions. So if you want to use the framework, if you want to contribute, now is a really good time. For example, a few months ago, I called out that Kotlin-inject doesn't support parameters. We like to have this pattern of a single scope annotation with different parameters like the app scope or logged-in scope that worked really nicely with Anvil. It didn't work with kotlin-inject, and instead we had to create separate annotations. This was a lot of boilerplate. The same thing applied for qualifiers for us, where we had to create type aliases. But now kotlin-inject supports qualifiers through annotations. So all these issues are gone now. So that's really a highlight. Things change and problems can be solved still. So make your voice heard if you want to use the framework. But there are also some bad things that I want to mention. First of all, you don't find as many resources online. If you want to learn more about kotlin-inject, you find a ton about Dagger 2, but not as much as kotlin-inject. But this will change, hopefully. That's why also people like me give talks about these frameworks. And then the other problem we have internally is that the releases are rather slow. Sometimes we fix bugs, discover bugs, and fix them in kotlin-inject, but it takes a while until there's a stable release. So we maintain a fork internally to adopt them faster. I want to go through some of the best practices that we adopted to make the framework work for us. For one, like I mentioned earlier, we create all the components in our final applications. And this is important because what is added to the final components differs. In this example, the app3 module and app2 module depend on forecast and weather, whereas the app1 only depends on weather. So the app1 application only imports the weather repository module, but not the weather component. That also determines what code will be generated. And we have these different applications that only import a subset of certain modules, and with that also a subset of the object graph. Scopes, we always add them to the classes themselves, never to the provider methods or the binding, in that sense, binding functions. We always keep this directly on the implementation because the implementation knows how it should be used, and that keeps it consistent for us. We use some naming conventions. Dagger modules are easier because they have an annotation. To clarify things for us, we name all the interfaces that have a provider function or get something out of the object graph component. So usually we have a descriptive name with the component suffix, and the same thing for provider functions. They have a prefix provide and then usually the return type, just to keep things consistent for us. If a class needs something out of the object graph, we adopted this pattern of defining internal classes like this component interface. In this case, our view renderer needs a coroutine dispatcher that's provided in our object graph. So we created this internal interface component that we then leverage. So that keeps the usage side close to the component. And then, in particular for Kotlin multi-platform, we create one component per platform. And what this allows us to do is provide platform-specific types in the object graph. For example, we want to have access to the Android application. And Android-specific code should be allowed to inject the Android application. And because of that, we have to create this component for Android specifically. And the main reason there is because the common code cannot access the application type. For iOS, we do the same. We provide the UI application object to our object graph. And then for desktop, there's no application class, so we don't provide anything. So these components start to differ a little bit. And then we have to repeat the same thing for the subcomponents, like our logged-in component, which has which accesses the Android app component. For iOS, we run into this case where we sometimes define types and interfaces in common Kotlin code, and the implementations actually live in Swift, but we create a single large framework for the iOS side, but then we have to provide the types from Swift in our object graph, and the object graph gets compiled and created during compilation of the Kotlin code. We solve this by having one interface, which we call iOS native implementations. And all it really is just an interface that becomes an argument for the component, and then it provides all the native implementations to the object graph, like you can see here. And with that, we started to see an issue that felt familiar to us because we've seen the same thing with Dagger 2, and that is that the boilerplate grows. We have all these components, and all of them have to be added as a super type to our final application component. And this list grows and grows and grows and keeps growing, and it becomes painful. It's even more painful if you want to introduce a new component interface that provides, for example, a new type. We have to add this new super type to all of our components, and we have multiple applications. We have, for each platform, a different application. So this became really a problem for us. And it was clear to us, what happened is we really missed Anvil and what it gave to us. And with that, I'm happy to announce that we open sourced finally our extensions that we built for kotlin-inject, which has the really boring name, kotlin-inject Anvil, but I think it gets the idea across. It really provides what Anvil did for the Dagger 2 for us, for kotlin-inject in Kotlin multi-platform. Not more and not less. I want to go through the example again from kotlin-inject, how it evolves, and it's very similar to how we change the Dagger code to Anvil. We can add a contributes binding annotation to our weather repository impl, and with that we can remove the component, and instead it gets generated at compile time. With that, we also have to remove the super type from our app component class. For the weather component interface from the forecast module, we just add a contributes to annotation. With that, we can also then remove the super type there on the application component. We have to evolve the app component annotations a little bit. We add a new annotation, merge component, and also then a new super type. There's a slight difference. It's only for the setup that you have to do once, but our extensions are built on KSP, similar to kotlin-inject itself. And KSP has the limitation that it can only generate new code and you cannot modify existing code. Anvil was a compiler plugin, so we had a little more magic going on because we had the ability to do that. But here we generate a new class and you have to manually add this as a super type. Then kotlin-inject Anvil provides some annotations out of the box. For example, I mentioned earlier, the kotlin-inject doesn't have a scope annotation by default. We provide this through an optional import that you can use. For example, we like this pattern with the single in annotation. We like to reuse our qualifiers, so we defined these already, and you can use them. And also a reference to the app scope. So by importing these, you can start using this framework out of the box without any extra code. Just what this does to our code, like I said, there's the singleton annotation. We no longer need this, and instead we use the add single in and provide the app scope. And you can see how this nicely aligns with kotlin-inject Anvil itself, where we have the contributes binding or the merge component annotations, which need to reference the scope. And that's pretty much it. It works the same way. We build our component. We still get errors at compile time in case we make a mistake. But then again, dependency injection was mostly out of our way, and the big benefit of aligning, and we got the big benefit back of aligning our build graph with our object graph at runtime. In our code base, we have a few custom annotations. That was another nice thing about Anvil. Anvil is extensible. You can create your own annotations and generate code for your own code base according to your own design patterns. And we had one such use case. We have these renderers that we call, and we provide these renderers to our object graph, find them at runtime, show content on the screen. I spoke about this last year, but the point here is that we had to write a lot of boilerplate code to make this work. This is roughly how it looks like in kotlin-inject, and nobody wanted to write this by hand. And that's why, from the beginning, we focused on making kotlin-inject Anvil extensible. And what we really wanted was just this, one custom annotation that we add to our renderers, and all the necessary code then gets generated. And it's easy to do, actually. And everything is built on KSP. There's no custom framework. So you can create your own simple processor. And all we really needed for this is support for KMP and multiple rounds, and both were supported by KSP, kotlin-inject, and our own extensions out of the box. A usual pattern to create a simple processor is you have a runtime module, and you have a compiler module, or your simple processor module. That's also the same way how our own extensions work. The runtime module is usually a Kotlin multi-platform module there, and it's just there for defining an annotation, like in our case, the contributes renderer annotation that we need. Small caveat here, in order to support incremental compilations and multiple rounds properly, we need to add one annotation. This will help then to defer compilation of components to later rounds. Something you don't need to worry really about. You only need to add this annotation that the Env extensions provide. The simple processor, the setup is very similar to most other simple processors, I want to say. Usually you just import the KSP APIs. You likely use Kotlin Poet because you want to generate some Kotlin code. And then for testing, we use the compile testing library for Kotlin. And we see this in a second. Defining a simple processor is straightforward. The documentation for KSP itself, by the way, is really good. But that's where we then get to our contribute renderer simple processor that we want to implement. Also here, I don't want to go into the details, but the pattern is usually always the same. You ask the APIs, give me all the classes that are annotated with a specific annotation. In our case, it's the contributes renderer annotation. Then we implement some checks. For example, we make sure that all these types are public because they get added to our object graph. And then in the end, we use Kotlin Poet to generate the component, which we can see here. It's typical Kotlin Poet. There's nothing groundbreaking here. The only thing I would like to highlight is that in order to support simple incremental compilation with KSP and simple processing properly, you have to tell KSP that generated code is associated with a specific source file. So if that source file changes, that then when KSP runs, it knows it has to invalidate this generated file, either recreate it or you have it will delete it for you entirely. That's the only connection you have to make, and which is important. Otherwise, you will see random build errors. For testing, that's a pattern we like to use. We define our source code in the tests themselves. Then we use Kotlin compile testing to to compile the code that makes also our simple processors run. And then we use the Java reflection APIs to verify that all the code has been generated. So the compile testing library, the nice thing about it is it gives you access to a class loader, and then you can rely on Java reflection. It helps us to make our tests more readable. And this is how it's implemented. It's typical Java reflection through the different class loaders. And with that, we pretty much implemented our custom annotation, which is specific to our code base. We didn't need to expose this anywhere in the open source project. And it worked really nicely for us to transition from Dagger to kotlin-inject in multi-platform code. I want to give a shout out to Chris Baines, who was an early adopter and gave feedback. Also, Zach Swears provided extensions for the circuit library from Slack. The feedback has been crucial, so kudos to them. Thank you very much. And with that, I'd like to wrap up. The point I'm trying to make here is that we didn't have to make, for our own extensions, our Env extensions, we didn't have to make any changes to kotlin-inject itself. The APIs, in that sense, are extensible. KSP is a great way for metaprogramming and generate code. It's very easy to use and supports things like multiple rounds and incremental compilation out of the box. So these are things you don't need to worry about. It's very accessible. And try to think about creative ways to extend the frameworks that you are using in your code base and try to make them work for you. Thank you very much.